Okay, so we're ready now to actually do the algebra of finding the derivative. In the last video we defined the derivative of the function, f prime of a, we say, right, as the limit as h approaches 0 of this expression here, better known as the difference quotient. And then there's the alternative way of defining this derivative. Okay, they're both going to yield the same result. We'll see sometimes one form is more preferable to the other. A lot of times it doesn't really matter. The point is, again, that we are going to do this algebraically, and remember the derivative has geometric meaning in the sense that the derivative is the value of the slope of the tangent line, or what we will eventually just call the slope of the function at a. Alright, so we're going to use both forms of this limit definition just to illustrate how they compare and evaluating some derivatives, which gives us the slope, and then we're actually going to find the equation of the tangent line. Now that we are able to find the slope and we have a point, we can find the actual equation, and that's a big accomplishment if you think about the big question we were trying to solve at the beginning of the semester, beginning of the course. Okay, so here's our function in this example, and we're going to find the derivative at a equal 1. I say a equal 1 because a is a fixed value here. So in this first one, we're going to assume right at a particular point. And so basically in the formulas above, everywhere I see an a is a constant. It's going to be 1. I'm going to replace it with 1. Okay? And then we'll find the equation of that tangent line. So let's use the first definition. By the way, sometimes I'll say the limit definition, but that is the definition of the derivative. I call the limit definition, but you will be required to show this work. Some of you have had calculus before and you know how to find derivatives a little bit differently, and we will get there, but you will have to find these derivatives by the limit definition at least once. So it is the limit as h goes to 0, right? F of what? A plus h. But what is a again? A is 1, so f of 1 plus h, right? So again, we're replacing a with 1 in each of these cases. Minus f of a, which is 1. So again, I'm plugging in there. All over just h. So I'm just using the limit definition. Now, when I look at this, notice if I plug in h equals 0, I get f of 1 minus f of 1, which is 0, over 0. Again, this is indeterminate, so this is where we're going to have to do some work. So first of all, we need to figure out what f of 1 plus h is and what f of 1 is. Well, f of 1, I can easily evaluate, right? F of 1, just plug into the function. And I get 3 minus 2 is 1, plus 1, I get 2. Right. And then what about f of 1 plus h? So let's write this out. The limit as h goes to 0. F of 1 plus h, I'm going to replace x with what? 1 plus h in the function. So be careful there. It's 3 times 1 plus h squared minus 2 times 1 plus h plus 1. Right? So this right here, I'll put that in brackets, right? That is f of 1 plus h. And minus what? F of 1. But I found f of 1 to be what? 2. All divided by h. Okay? And so again, if I plug in h equals 0, you're going to get 0 over 0. Still in determinate form. So we've got to do some work. And so these are the types of limits we've been working with, and we want to evaluate this limit algebraically. So I'm going to do some cleaning up here. First of all, I'm going to square 1 plus h, and when I square 1 plus h, what am I going to get when I square 1 plus h? Am I going to get 1 plus h squared? No. Everyone should know by this time I get 1 plus 2h plus h squared. So be real careful there. When I distribute that 3 through, then I get 3 plus 3 times 2, 6h plus 3 times h squared. Here, notice I've got a negative 2. Distributing that through becomes minus 2 minus 2h plus 1 minus 2. To close that off, now I just need to simplify up top by combining some like terms. Notice I get 3 minus 2 is 1, plus 1 is 2, minus 2 is 0. So our constant terms, I'm just going to sort of scratch those out, they combine to 0. Okay? And then I've got a 6h minus 2h. 6 minus 2, 4h, plus 3h squared, and that's it. Except I've done something terribly wrong, right? I'll harp on it. I forgot my limit sign. When I say use correct limit notation, this is what you should be doing. Right? Keeping that limit sign. It is not correct to write it without the limit sign because I haven't taken the limit yet. I'm just simplifying. Even now, I can't plug in directly to evaluate because if I plug in h equals 0, I get 0 over 0. But now we see our problem. If I factor out that h from the numerator, leaving me a 4 plus 3h, I get the limit as h goes to 0 of what? These h's cancel. I'm just left with 4 plus 3h. And what is that? 4 plus 3 times 0. I can plug in directly without any problem, and I get 4 as my limit. Notice once I plug in h is 0, I don't have the limit sign anymore. There's no limit. Once you do the direct substitution, you don't need the limit. So there is, we found this limit, it exists, and that tells me the slope of the tangent line at x equal 1 is 4. Okay. Just for comparison, let's take a look at the alternate way of defining the limit, which is with this form. F prime of a is x minus, as the limit as x approaches a, f of x minus f of a divided by x minus a. So let's look at the alternate definition, just compare the two. We're going to get the same result. So here f prime of 1 is the limit as x approaches a, and what is a in this case? 1. F of x minus f of a again is 1, over x minus a, which is 1. Again, I want to replace the a with the point what we're talking about. Okay, f of 1 we already evaluated was 2, and so let's see what we have here. This is the limit as x approaches 1. F of x, remember, is just our function, 3x squared minus 2x plus 1, minus f of 1, which we said was 2. If I plug in directly, I still get 0 over 0. Let's do a little simplifying, though. 3x squared minus 2x, 1 minus 2 is a negative 1. Okay. I know, again, if I plug in x equal 1, I'm going to get 0 over 0. You can see that. And, of course, what does that mean? How do I evaluate that limit? We're going to have to factor, right? There's obviously a factor of x minus 1 up top here. What's the other factor got to be? Well, I've got a 3x squared. That's going to have to be 3x. And then the last is negative 1, so this has to be a plus 1. Let's make sure that works. X times 3x is 3x squared. The outer is positive x. The inner is negative 3x. That combines together to give me negative 2x. Last times last is negative 1. So again, I've got to be able to factor. But now, notice this common factor of x minus 1 simplifies down to just 3x plus 1. And I can plug in directly now. Notice the limit sign is gone, and I get 3 plus 1, which is equal to 4. Right? And so I get the same thing that I got above, obviously. Okay? So which form of the definition do you like better? Which algebra seems simpler? Okay. I'll let you make the choice, right? Maybe you think they're about the same. Maybe you think one is better than the other. Okay. So not significantly different, but there is some difference there. Okay, so now that we have this, let's find the equation of the tangent line. So the slope, SL, spelling spoke, the slope of tangent line at x equal 1 is f prime of 1, which we found to be 4. There's our slope, right? That's our slope. And what about the point of tangency? In other words, what is the point on the function itself where this tangent line is passing through? Well, it's 1 comma f of 1. So I need to know the actual point on the function itself. And you remember up above we said f of 1 was what? 2. If you look up above it was 2. So 1 comma 2 is our point of tangency. And so what's our tangent line going to be? Remember the point slope form of a line? Right? And our m here is 4. And here's our given point. And so I've got y1 is 2, m is 4, x minus x1. And then we probably might want to solve for y. Let's do that by distributing the 4. I get 4x minus 4. There's a minus 1 there. Hard to see that. So 4x minus 4, and then I can add 2 to both sides, right? And I get y is equal to 4x. Negative 4 plus 2 is negative 2. And there is the equation of my tangent line. Now, there's a lot going on in this process, right? We got the limit definition. We're doing a lot of manipulations algebraically, factoring, simplifying, and then here we're plugging in, we're distributing. We can make little mistakes, and that happens. Do we have any recourse? Do we have any way of checking that this is indeed correct? Well, yeah. We've been, in the last video, we talked about geometrically how to estimate the slope of the tangent line, how to estimate the derivative, and it was by sketching the tangent line. So this line should look like it's tangent to the original function at x equal 1. Okay, so let's take a look. I've actually graphed the original function in a solid line. This is the original function. Remember that was f of x equals 3x squared minus 2x plus 1. That was the original function. And this dashed line, that is our tangent line. This is the line y is equal to 4x minus 2. Okay, the slope is 2 for every, the slope is 4. For every 1 we go over, we go up 1, 2, 3, 4, right? And that's the slope of that line. Does it look like it's tangent to the graph of the function right there? Yeah, does it look like it just touches the graph there locally? Yeah, it sure does, right at the top of my ruler. So we feel confident that we have accurately found the equation of the tangent line, right? If you do your work and you get your equation of your tangent line and you graph it and it looks more like this, passes through the point, but it's clearly not tangent, something's wrong. You've done something wrong. Or worse, if your line's like way over here, not even passing through the graph, something's really wrong. So we do have a way of checking and verifying graphically. Okay. Let's look at another example. One more example here. Let's do the same thing with this function. A little more challenging example here. Let's get those definitions again up at the top of the page there so we can see how to do this. So here's our function. We're going to find f prime of 2 this time. So in the formulas, our value of a this time is 2, right? So first of all, with the derivative definition up top, f prime of 2 is the limit as h goes to 0. A is equal to what again? 2, so this is f of 2 plus h minus f of 2 all over h. And let's just find f of 2, shall we? F of 2 is what? 5 divided by 2 times 2 minus 1, replacing x with 2. And 2 times 2 is 4, 4 minus 1 is 3, I get 5/3. And let me just go ahead and evaluate f of 2 plus h then. That's 5 divided by 2 times x, where x is what? 2 plus h minus 1. So if I distribute that 2, this part right here becomes 4, 2 times 2 plus 2h, and then a 4 minus 1. 4 minus 1 is 3. So this becomes 5 over 2h plus 3, or 3 plus 2h. Okay, so now let's plug those values in, and let's see what we get. F of 2 plus h, we said, was 5 divided by 2h plus 3 minus f of 2, which is 5/3, all over h. Okay. So all this stuff here is what we use to plug in those values. And now if I plug in directly h is 0, I'm going to get up top 5/3 minus 5/3, which is 0. 0 on the bottom, so again, I'm in indeterminate form. So do you remember how we evaluated limits involving what fractions within fractions? We cleared out the fractions, the smaller fractions. And so I'm going to do that by that second technique I showed you. I'm going to multiply the numerator and denominator by the least common denominator of all my smaller fractions. Denominator here is 2h plus 3. Denominator here is 3. Denominator here is 1 if you want to think about it, h over 1. So I'm just going to multiply by the product 3 times 2h plus 3 in the numerator and in the denominator. So I'm multiplying by a grand total of how much? 1. Right? Not changing the expression at all. So the limit as h goes to 0. Now I distribute across the top here the 3 times 2h plus 3. The 2h plus 3's are going to cancel, leaving me 3 times 5 is 15. Here the 3's will cancel, leaving negative 5 times the parentheses 2h plus 3 quantity. Down below, I'm just going to multiply all these together. H times 3, or 3h times 2h plus 3. I could distribute that through, but again, I want to leave it factored because I'm going to be looking for a common factor to simplify this expression so I can evaluate the limit. Okay. Well, up top, can we do some simplifying here? Yeah, I got 15 minus 5, distributing that minus 5, 5 times 2, 10h, and then be careful here, negative 5 times positive 3, that's negative 15. So what does that top all simplify down to? 15 minus 10h minus 15. The 15's go to 0. I'm just left with negative 10h. And so these h's now, there's that common factor I'm looking for, right? And when I get rid of that h in the denominator like that, by canceling with the h in the numerator and simplifying, I can now plug in directly, right? And when I plug in directly, what do we get? Up top, I just have negative 10. Down below, I've got 3 times 2 times 0 plus 3. And what's this? 2 times 0 is 0, plus 3 is 3. 3 times 3 is 9. So this is negative 10 ninths. Okay. All right. Let's look at the alternative definition. Let's look at the alternative definition. So that's this one here. F prime of A is the limit as x approaches A. If you remember, again, A is 2. So it's the limit as x approaches A, or 2. And it's going to be f of x minus f of A, where A again is 2, over x minus A, where again A is 2. So what do we get? F of x is just the original function. Go back up to that, right? 5 divided by quantity 2x minus 1 minus f of 2. And what was f of 2? We found that up here. F of 2 is what? 5/3. All over x minus 2. If I plug in directly x is 2 up top, I get 2 times 2 is 4 minus 1 is 3. I get 5/3 minus 5/3. That's 0. 2 minus 2 is 0. So again, indeterminate form. But the way we're going to clean this out this time, again, fractions within fractions, I'm going to multiply the least common denominator of all fractions, 2x minus 1 and 3, so I'm going to multiply by 3 times the quantity 2x minus 1. And that will clear out my fractions, top and bottom, so the total amount I'm multiplying by is 1. So the limit as x approaches 2. Here the 2x minus 1's cancel when we multiply this by distributing through again. The 2x minus 1's cancel, I'm left with 5 times 3, that's 15. And then the 3's cancel, leaving me minus 5 times the quantity 2x minus 1. Down below I do have to multiply all these together, so I've got 3, let's pull that in the front, times the quantity x minus 2, put that in parentheses, 2x minus 1. Again, don't FOIL all this out, I'm going to leave the denominator factor. But up top I can do a little simplifying, right? Let's look at the very top here. Got 15, distribute this minus 5 through, I get negative 5 times 2, negative 10x, negative 5 times a negative 1, negative times negative, positive 5. So what does the top simplify down to? So the top simplify down to, let's see, what do I have? I'll have a negative 10x, 15 plus 5, plus 20. Okay. And of course, when I plug in x equal 2, I'm still indeterminate because the top is 0 and the bottom is 0. But I notice that I can factor the top. What can I do factoring up top? Greatest common factor of negative 10. Why pull out a negative? Well, I like to have my x term to be positive, and you'll see why here in a minute. When I factor out the negative 10, what's that going to leave me? X, what? To get this to be positive, now I need minus what? 2. Negative 10 times negative 2 is positive 20. So that's the top factored. And the reason I did the negative 10 is because I wanted to have that x minus 2 factor. Right, that x minus 2 factor, and I can now cancel in the numerator and denominator. Right? And the equivalent expression is negative 10 divided by 3 times the quantity 2x minus 1. And I can now plug in directly. X is equal to 2. 2x is 2 minus 1. Right, plug in x is 2. Notice there's no limit sign anymore. And I just simplify this expression. 4 minus 1 is 3. 3 times 3 is 9. I get negative 10 ninths, which of course is exactly what I had up above. Okay. Again, which technique do you like? Do you like the alternate definition here, or do you like the original definition? Okay. We've done 2 examples. Maybe in one definition seems simpler than the other. Maybe they both seem about the same. Okay, we're mostly going to be using this. We'll mostly be using this definition. The alternate definition we'll use later on when we talk about derivatives from the left and from the right. Let's go ahead and find the equation of the tangent line to the graph at this point. So we've found the slope is negative 10 ninths, and a point of tangency, which is what, the point 2 comma f of 2. You remember we found f of 2 to be 5/3. And so I've got y minus y1, so here's x1, y1, so that's 5/3, is equal to m, which is negative 10 ninths, x minus x1. So that's plugging it into the point slope form. So here's m, here's x1, y1. There's the equation of the tangent line. Solve for y to make it a little bit nicer, and I'm going to distribute the negative 10 ninths, so I get negative 10 ninths x, negative times negative, positive 10 times 2, 20 ninths, and then I want to add 5/3. And when I add 5/3 to 20 ninths, I need a common denominator, don't I? 20 ninths plus 5/3. Common denominator is 9. So I get 20 ninths plus what? Multiply top and bottom by 3. 15 ninths. 15 ninths and 20 ninths is 35 ninths. Okay. And there's the equation of the tangent line. To the function f at x equal 2. Again, you can check graphically like we did in the previous example and confirm does that actually look tangent to the original function at x equal 2. To close, I want to make two general observations about the derivative. So far, we've looked at the derivative just at a point. What we want to transition to in the next lecture is the derivative as a function. And I want you to say if f of x equals c, right, for some real number, if we're looking at that function, find an expression for f prime of x. Well, I think you already know the answer to it. What's the graph of the function f of x equals c look like if I were to graph that function? Everyone should be saying it's a horizontal line. So let's say c is a positive number, just for this illustration. If c is some positive number, then the graph of the function will just be this horizontal line. Right. No matter what the input is, the output's always c. So f of 0 is c, f of 1 is c, f of 2 is c, f of 3.7 is c, and so on. And if you look at any tangent line, if I were to find the line, tangent for any value of a, let's say a is this value, what's the slope of the graph at that point? Well, if I try and just touch that point, notice that the tangent line is going to coincide with my function. It's going to be a line as well, right? It's going to coincide. It's going to be horizontal, and the slope is obviously going to be 0. The slope of this line is 0. Therefore, the tangent line must have a slope of 0. Okay? So we know it has to be 0. Let's just prove it with the limit definition. And this time, instead of using a, I'm just going to use x. I'm going to say the limit, I'm going to let a be any real number x. Okay, so it's a limit as h goes to 0, f of a, but I'm going to let that be x plus h, minus f of a, or f of x, over h. And the reason I can do that is here, what's f of x plus h in this case? F of x is always c, so what's f of x plus h? Answer, c, right? No matter what the input is, what's the output? C. F of x is c, f of x plus h is c, f of a is c, right? Everything. F of x, of course, is c. And if I simplify, what's c minus c? C minus c is 0. What's 0 divided by h? 0 divided by h is 0. What's the limit as h goes to 0 of 0? It's a constant function, so the limit is just that constant 0. And that's exactly what we realize, right? So that for any constant function, the derivative, which is the slope, is going to be 0. Well, if we move one step further, what's the derivative going to be for the function f of x equals mx plus b for some real numbers m and b? So you should recognize this as a linear function. And what's the slope of this line? M. So what should the derivative be equal to at any point on this line? It should be m, right? Because the tangent line will coincide with the line in this case. Let's just confirm that. We're going to let a be the variable x in this case. The limit as h goes to 0, f of a, or x plus h, minus f of x over h. Now it's going to be a little trickier here than the last one, because now when I plug into the function x plus h, forget I've got this limit, x plus h, I've got m times the quantity x plus h plus b, that's f of x plus h, minus f of x, which is just mx plus b. And so I've replaced x with x plus h here, of course x with x, and I get mx plus b. So now I need to, of course, if I plug in h equals 0, I'm still indeterminate, 0 over 0. But if I simplify here, I get mx plus mh plus b, and then distribute this negative, negative mx negative b, what does the top simplify down to? Mx minus mx is 0, b minus b is 0. We're just left with mh up top divided by h. What's mh divided by h? It's just m. And what's the limit as h approaches 0 of m? M is a constant. Notice h is the one that's going to 0. We just get m, which is what we suspected, right? The slope of any line, or the tangent line rather, to any linear function is equal to the slope of that linear function, is equal to the slope of that line. Okay? So this is where we're going to go to. So a lot of functions aren't lines, right? X squared is not a line, sine of x is not a line, square root of x is not a line. And so those functions, the derivative will change. It won't be constant. It won't be equal to a fixed number like it is here. And so we're going to have to look at those, and we want to look at those then from the standpoint of the derivative now as a function itself. And so that's where we're going to go next. We're going to look at the derivative as a function.